In this video, we're going to be simplifying some square roots using the product rule. We'll talk about rational and irrational square roots and how we can simplify irrational square roots using what's called radical form. First, before we get into that, let's talk about perfect squares and perfect square roots. When you square a number, that means that you are multiplying it by itself and you are raising it to a power of 2. So 1 times 1 is 1, 2 times 2 is 4, and so on through this list of numbers 1 through 12. Definitely know these perfect squares because square roots are just working backwards from this list. So if you know your perfect squares and you can think backwards, then you'll know your perfect square roots. For example, if I know that 7 squared, or 7 times 7 is 49, then we should be able to see that the square root of 49 is 7. Square roots are saying what number times itself is this value. So we're thinking backwards of squares. So if you know your squares 1 through 12, and hopefully know your perfect square roots in reverse, then you'll be all right. It's even better if you can go up a little bit more on that list and do 13, 14, and 15 squared and its corresponding square roots. For the most part, those are the ones that you work with the most. Let's talk about the difference between a rational and an irrational radical. Rational radicals, well, first of all, a radical is this symbol. There's lots of different types. There's a square root, and there's a cube root and a fourth root, and you can keep going up and have as many types of roots as you want. So the radical is just that symbol. And if I evaluate a rational radical, that means when I evaluate something in this form, I get a nice whole number. So these are all examples of rational radicals. The in-between numbers are what we call irrational radicals. So if I try and take the square root of 2, you can try it out on your calculator. It gives you a decimal that doesn't ever end. And so we call that an irrational number. And so in between all of your perfect roots are irrational roots. And there's a way to simplify those that we'll get to. Let's talk about this product property for radicals. If I have two numbers being multiplied under a radical, I'm allowed to separate them and give them their own radical. And we could start here and work backwards. If I'm given two numbers that have their own separate radicals, as long as they're the same radical, then I'm allowed to put them under the same radical. So for instance, if I had a square root of a number and a cube root of a number, I'm not allowed to do this. But as long as they're both square roots, we can put them under the same square root radical and hopefully simplify. So either this form or this form will make simplifying a little bit easier. So let's practice that. Here's some steps to help us with some irrational radicals. What we want to do is factor this number that's inside the radical. And we either want to factor it into two numbers that are perfect squares, or one factor that's a perfect square, or we can factor it all the way down to its prime factors and look for pairs of prime factors. I can simplify or take out pairs of prime factors, or I can take out roots of perfect squares. So we'll see what that looks like. Anything that hops out of a radical or simplifies out of a radical is multiplied by anything that's already out front. And we'll see what that looks like. So let's work through these steps in the following examples. If I want to find the square root of 12, this is an irrational square root. So what we have to do is break 12 down into some factors that we can take square roots of. So if I factor 12 into 4 times 3, I'm allowed to simplify this by taking the square root of 4. I can't take the square root of 3, I can't simplify it anymore. So the square root of 4 is 2. That gets multiplied out in the front, and it leaves behind the square root of 3. So this is called a simplified radical form because we kept that radical symbol. We could have done it using prime factors. If we had factored 12 all the way down to its prime factors, that's 2 times 2 times 3. And we take out pairs and just write one of them out in the front. So we'd get the same answer. Let's do this example. 2 times the square root of 8. Well, the square root of 8 is an irrational radical. We got to factor it. You could factor it into a 4 times 2, break it apart, and say we know the square root of 4 is 2, so I have 2 times 2 here, and that's 4. And we're left with that radical 2 or square root 2. We could have done it using prime factors, factor 8 down all the way into 2 times 2 times 2, and cross off this pair right here, take one of them out, multiply it with that 2 in the front, and it leaves behind a 2 still under the radical, so we get the same answer. One more time. Let's try and simplify the square root of 56. If you know that 4 times 14 is 56, then that would be that perfect square factor. And we could just take the square root of 4, which is 2, put it at the front, and keep the square root of 14 under the radical. Because we can't simplify that, the only factors of 14 are 7 and 2, so both prime numbers that we can't factor, so we'll just keep it at 14. If you didn't know that, you could have factored 56 down into 2 times 2 times 2 times 7, and taking that pair of 2's out, just wrote one of them at the front, and 2 times 7 stayed under the radical. Sometimes we try and square square roots, or take the square root of a square. So if we understand this property, it makes simplifying a lot easier, and we don't have to go through all of the small mini steps. If you know that squares and square roots are what's called inverse operations, then they just cancel each other out. So if I'm trying to take the square root of 13 squared, well, the square root and the power of 2 cancel each other, and we're just left with 13. Same thing over here. If I want to square a square root, well, again, the power of 2 and the square root cancel each other out, and we're just left with 8. Sometimes we're squaring binomials that have square roots or other types of radicals. Remember that a square of something that's many terms means that we're multiplying this by itself. So it's not just 2 squared times the square root of 5. It's 2 times the square root of 5 times 2 times the square root of 5. So sometimes rewriting it so that you can see that you're multiplying it by itself helps you simplify. We got 2 times 2 at the front, that's 4. The square root of 5 times the square root of 5 is the square root of 5 squared, and we're just left with 5. So now we have 4 times 5, which is 20. Eventually, you want to get so good at these that you can just do a lot of this in your head using mental math, and hopefully not have to walk through all these little mini steps. So if you know your perfect squares, hopefully you can just say the square root of 64 is 8. If you get used to factoring numbers and getting used to what their perfect square factors are, then hopefully you can jump from the square root of 32 straight to 4 times the square root of 2, because you know that 16 times 2 is 32, and the square root of 16 is 4. And then again, when we're squaring binomials with radicals, think about it multiplied by itself in your head. We're doing 3 times 3, and the square root of 7 times the square root of 7. So that is 3. Sorry, that's 9 times 7. Ooh, there's a little typo. So 3 times 3 is 9. 9 times 7 should be 63. Make sure you make that correction there. All right, so that's simplifying rational and irrational square roots.